Okay, this will be Chapter 7, Lesson 4. And here we're going to begin talking about, we've been talking about metals last lesson. So here we're going to discuss some common ionic charges that's formed by the elements on the periodic table. Now, a good amount of this should be familiar to you from Chemistry 1, most notably the fact that the S group metal ions are essentially in the alkali metals group, this first group, all form a +1 charge. And essentially the reason for that is because they will lose one electron in their highest shell to become like the noble gases. Similarly with the group 2 metals, they'll form a +2 charge. And then the halogens, a -1 charge, the oxygen group a -2 charge, and the nitrogen group predominantly a -3 charge. Now these are full charges. However, what we have not discussed is the idea that kind of the pattern to the D block metal ions, including some of the P block metallic elements down toward the bottom. So the idea is it's always true that the electron configuration will predict ion formation. So we can see that easily with magnesium, how it's going to lose its 2 s electrons, its 2 3s electrons, that is to say, to become just like the noble gas neon. Its core electrons will then determine its electron or its charge. And so likewise we can take a look at something like scandium here. Now scandium has a +3 charge, you'll notice. And to rationalize that, what we'll say is that scandium, which has the noble gas configuration of krypton, let's see here, or I'm sorry, argon, and then we have 4s2 and 3d1. So scandium will have 3 electrons to lose, and that's why it has a +3 charge. Titanium will do likewise. It'll lose its 2s and 2d electrons to become a +4 charge. Vanadium can, the top one here, by the way, will be the most common one. So this is the more common one. Likewise for the rest of the ones in the D block. Vanadium will lose 3 from the D, 2 from the S, and give you a +5 charge. Then a chromium will give you a +3 charge. It turns out losing more than 5 electrons is extremely difficult and creates a very unstable ion. So most of these will actually be +3 or +2 as we move along the D block. So the two most common charges are +2 and +3 among these. You can see that for example, in the case of iron, take a look at iron, try to rationalize some of these charges with iron. Iron can have a +2 or a +3 charge. The +2 charge comes from losing its 4s electrons, 2 of its 4s electrons, and the +3 charge comes from losing, in addition to the 4s electrons, one of the 3d electrons. So instead of 3d6, iron will actually lose one of these to become half filled. Again, the stability to become a 3d5 subshell. So you can kind of see the rationale behind some of these. Nickel and cobalt are predominantly +2. You notice here that copper, silver, and gold all form a +1 charge. And recall that we talked about how these their electron configurations for copper, if you recall, was an exception. It had argon, and then it had 4s1, and then 3d10. So what happens for these three, they will lose their 1 electron, and 1 s electron to become a +1 charge. That's why the most common charge for this group is a +1 charge. For the zinc group, it's all +2 charge because they have a fully filled D subshell, so all they do is lose 2 electrons. So again, you can rationalize, if you write out the electron configuration, you can really rationalize some of these trends in the D block. I do want you to keep track of these. This group is also very easy to rationalize. Even though tin and lead and antimony and bismuth, they are in the P block, they do act much like the D block. So they can form more than one charge. And again, you can rationalize it here. Tin will lose, to form a +2 charge, will lose 2 of its s electrons. To form a +4 charge, it'll lose 2 s and 2 p electrons. Likewise, with antimony here, it'll lose 3 of its p, or 3p and 2s, to give a total of a +5 charge. So again, I want you guys to be able to rationalize, even though it may not be a perfect explanation, but be able to rationalize some of these. And what this says, this is essentially kind of a reiteration of it, but whenever electrons are removed or electrons are lost, we always remove them from in the order of decreasing n, which means from the highest energy level first. So if you take a look at zinc's configuration, if we have to, zinc will form a +2 charge. So what we'll do is we'll lose the highest, the 4s electrons. This is the highest energy level. We fill the 4s and then the 3d, but we lose the 4s, and that's kind of been the rule, and that's able to explain a lot of these common charges. So for iron, for example, for the +2 charge, we'll just lose the 4s electrons, and then again, like we talked, for the +3 charge, you'll lose 1 from the d to get a half-filled shell, or I'm sorry, half-filled subshell. And then we talked about silver losing just this 1s because of the exception. So the most important thing, whenever you're writing, you can write electron configurations for these, you'll remove them from the highest shell first. And that's exactly what we'd like to do here. So if you take a look at cobalt, we want to write the configuration for the cobalt ion. So firstly, let's go ahead and write out the full configuration of cobalt, and have your favorite periodic table next to you to consult. Here cobalt is. And so what we'll do is we'll do argon, we'll do 4s2, and then 3d, 1, 2, 3, 4, 5, 6, 7, 3d7. So this is regular cobalt. So we got argon, 4s2, and 3d7. If we want to now write the ion, the cobalt +3 ion, what we'll do is we'll lose 2 from here, and then we'll lose 1 of these and become 6 is the idea. We always lose from the highest level first, and then from the lower level. So we'll end up being argon 3d6. This will be cobalt's cobalt 3+ electron configuration. And you can do likewise if you have something in the p block, because the p block, if you take a look maybe at something like phosphorus, or because phosphorus won't necessarily lose, it'll rather gain. Take a look at maybe at something like tin. Let's take a look at tin. Tin has chromium. Let's take a look at tin. So tin has chromium, I'm sorry, not chromium, krypton, for its noble gas. And then we have down here 5s2, 4d10, and then 5p2. So for tin, it'll first lose these electrons, the 5p, because the 5 is the highest energy level, and the p subshell is higher than the s subshell. So we'll first lose these 2, and then we'll lose these 2. That's kind of the idea. So hopefully you can now write electron configurations of ions. Moving on, we're going to sample different portions of the periodic table along with the corresponding chemistry. So let's take a quick look at metalloids first. And these are the semimetals that sit between both metals and nonmetals. And they're called metalloids because they have characteristics essentially of both metals and nonmetals. The most notable of these is actually silicon. If you take a look at silicon, it is nice and shiny like a metal, but it's very brittle. It'll break. If you drop it on the ground, it'll actually easily break into little shards, much like a nonmetal would. Like you can make nonmetals into powders, and it's a fairly poor conductor. In fact, silicon is used in the semiconductor industry, which is especially in making computer chips, because it's able to conduct and not conduct at the same time. We can actually set up a computer code for it, and that's what the zeros and ones are based on. Its ability to conduct and not conduct at the same time, to do both. That's silicon, and really all the metalloids. Let's take a quick look at the alkali metals. So interestingly, alkaline metals are all soft. This shows sodium being cut with a regular kitchen knife. They have low densities and low melting points. It's actually quite easy to melt them. And the reactivity of these increases as you move down the group. This is actually an important trend. So as we move down the group of the periodic table, their reactivity increases. And this is due to the fact that it becomes easier and easier to remove the outer electron because the outer electron is further away. It's removed more easily, therefore the metal is more reactive. One of the more famous equations for you to remember is the reaction of the alkali metal with water to form their corresponding metal hydroxide. So if you take a look, in this case we have the metal reacting with water to produce the metal hydroxide, and then hydrogen gas is evolved. The way to think of this one is actually to think of it as a single replacement reaction. So think of sodium here, for example, reacting with water. Let's write water as HOH, and you'll be able to see the reasoning behind this. And so what you could see is that the sodium replaces the hydrogen replaces the sodium, and you get yourself sodium hydroxide and hydrogen gas. So think of this one as a single replacement reaction, and it'll be easier to remember. You form the metal hydroxide, but you also form hydrogen gas. Very important. Alkali metals can react directly with all nonmetals, most notably oxygen. Obviously, when you're reacting with oxygen, you'll just produce the oxide of that metal. This is the most common product. However, by altering the reacting conditions, you can actually form what's called a peroxide, and we've mentioned these a little bit earlier. This is where the charge of oxygen is -1. In rare circumstances, if you rig the reaction just right, you can actually form a superoxide. In this case, if you analyze the charge of oxygen, oxygen has a charge of -0.5, which is really strange, but it makes it, superoxides are very reactive, peroxides are also very reactive, and your oxide is the most stable form of the metal oxide. As a general rule, the salts of alkaline metals, or really the ionic compounds of alkaline metals, will be colorless. And this is actually another confirmation of the idea of energy levels and electrons and subshells, because since they are colorless, all the alkaline metals, whether it was sodium chloride, calcium iodide, all of these are colorless. Their transition metal salts are actually colored. In fact, here you see this is nickel chloride. This is nice and colored. This one here is actually iron oxide, Fe2O3, iron 3 oxide, and this one is your good old sodium chloride, or you can substitute it, for calcium iodide, really any substance, but they'll be colorless. And this is because a D metal ion, or whenever it becomes an ion, still has electrons left in its D subshell to further excite. In fact, with iron oxide, iron here is a +3 charge, and the +3 iron, we could show it up here, still has the configuration of argon 3d5. So there are still electrons in the D subshell to excite. Unlike sodium, or really any other alkaline metal, it does not have. It just has the noble gas configuration and no extra electrons to excite. This is a neat experimental confirmation. In fact, what you could do is you can get the alkaline metal compounds to give their colors if you burn them. So what will happen then is the flame will reduce the ion, meaning it will allow the ion to receive some electrons back, and as it gets reduced, those electrons that go back to its original shell can now express themselves and give a color. Most notably here, lithium is a famously red color, gives a famously red color in the flame. Sodium gives a famously orange color, and potassium a famously purple color. And hopefully you've enjoyed burning some metal ions in Chemistry 1 in the flame test, but this would be a flame test. Let's talk a little bit about the second group, the alkaline earth metals. Similarly to the alkaline metals, their chemistry is similar, except that they'll gain 2 electrons, or not gain, but they'll lose 2 electrons, forming a +2 charge. In general, they are harder, a little more dense than the alkaline metals, and here you can see some reactions directly with nonmetals. So magnesium with chlorine produces the characteristic magnesium chloride. Similarly, magnesium with oxygen, magnesium oxide. So hopefully you've come to expect these synthesis reactions. The reactivity of these, just like with the alkali metals, will increase as you go down a group. An example of this is magnesium, which will react with hot water, or react with steam, but not with regular water. Beryllium, for example, does not react with water. It's quite stable. But as you go down to calcium, you can actually throw calcium in water. This is a calcium thrown in water. It'll actually produce hydrogen gas just with cold water. So calcium is pretty reactive. And their salts are also colorless because their outer shell electrons are lost. No more outer shell electrons left. Let's take a quick look at hydrogen. This should be something familiar to you, but hydrogen is a colorless diatomic gas. And hydrogen can do both things. Hydrogen can accept an electron, or it can lose an electron. It'll accept an electron whenever it's reacting with metals. So you form what's called a metal hydride. In this case, we form sodium hydride. In this case, hydrogen must have a -1 charge, because metals will always have a positive charge. When it reacts with the nonmetals, hydrogen will have a positive charge, as in the case of water. Recall that H plus is just a proton, and a proton is the important characteristic, or the important player in an acid. Acids actually release protons, so acids are what an H plus is. Let's take a look at carbon, another very interesting element that we should mention. Carbon is what life is based on, what life is built around. This is, if we were to take you and dry you up, you would probably protest, but after a little while you'll stop protesting, and then we'll be able to analyze the makeup of what you are, and once the water has been removed, we'll find a boatload of carbon. In fact, your body, whether your hair, your skin, your cells, is all based on carbon. So organic chemistry is the study of pharmaceuticals or drugs that interact with the body. And then biochemistry would be something that studies how those molecules interact on the larger scale with the body. And all of these are based on good old carbon. And the reason carbon the reason why life is based on carbon is because of carbon's ability to form very long chains, 4 bonds to each, and this gives us really an infinite number of compounds, an infinite number of possibilities. So carbon is extremely important. Let's take a quick look at the oxygen group. Let me introduce you to the term allotropes. The word allotrope means a different form of the element. And there are 2 different elemental forms of oxygen. The O2 you're aware of, but the ozone you may have been less aware of. Ozone is actually a very important substance that protects us from the dangerous sun rays, ultraviolet rays, in the upper levels of our atmosphere. And ozone has been produced on the Earth. It's a pretty toxic substance. And it's a very strong oxidizer, which means it'll pull electrons from other substances, oxidizing them, is the idea. And here's a little picture for you of ozone for your visual pleasure. Sulfur, this is also in the oxygen group. Sulfur is a very interesting thing about sulfur is in the elemental state, it'll actually form these rings of S8. Kind of looks like a crown. It'll form these molecules, stable molecules. And actually it's a pretty neat thing to do. You can heat the sulfur up and it'll melt, and then it'll form these neat rings. Going down, the oxygen group, selenium is still a nonmetal. Tellurium is your metalloid or semi-metal. And polonium technically is a metal, but it's pretty radioactive and not as useful. Let's say a few things about the halogens. They are all diatomic. The reactivity increases going up the group. This is different from alkali metals and alkaline earth metals. So fluorine, for example, is your most reactive most reactive nonmetal. Well, I think we got it down here. So fluorine is your most reactive nonmetal. Let's just underline it. Here, what you see here, this is good old bromine. This is iodine. And this looks like fluorine. Fluorine notoriously is very difficult to contain, and it actually will eat away at glass. So very hard to contain. But what you could see is that you can also see the reaction of these halogens. They're pretty reactive. They'll react almost with any other element. In the case, they'll even easily react with water to give you hydrofluoric acid and oxygen. You can think of this as a single replacement reaction as well. Chlorine is also reacts with water, and this is famously done in pools to chlorinate pools, to disinfect pools. That way all those little microorganisms that are swimming around do not multiply and cause you an unpleasant stay at the pool. And it also disinfects anything that you decide to put inside the pool against the county regulations. It's able to essentially disinfect it. And so chlorine will produce hydrochloric acid, small amounts of this, but more importantly, hypochlorous acid. This is hypochlorous acid. And this is really a really weak acid that's able to keep track of the microorganisms and take care of them. Little tiny bugs. If it's a big bug, like this young one, the big bug stays alive. Little tiny bugs go down. Let's take a look at bromine. Bromine is among one of the most interesting nonmetals in the periodic table because it is a liquid, famously red liquid. Very reactive. Because it's a liquid, if you throw anything into a little vial of bromine, it's extremely reactive. Fluorine is more reactive, but fluorine is a gas. It's not as dense and not as concentrated, so its reactivity is essentially reduced because of that. Iodine is a solid, but iodine sublimates at room temperature. So if you just leave it, you can actually see it becoming a gas in front of your eyes. It does not go through the liquid state. Astatine is not too much well known. You can't have too much fun with astatine as it is radioactive. And then finally, let's say a few things about noble gases. It's famously known that noble gases are unreactive, and it's a good idea to remember the reason for their unreactiveness, and that's because they have a completely filled both S and P subshell, or you can say completely filled shell is the idea. So some of the noble gases rarely do react. Humans have been able to make them react, and most notably forming fluoride compounds. You'll notice that most of the compounds that are formed are from fluorine, and that's because fluorine is one of the most reactive compounds. Notice even krypton difluoride was able to be synthesized with fluorine, and pretty recently, this compound has been made involving argon. Argon, as you go up the periodic table, it becomes tougher and tougher to react the noble gases. Going down, notice that xenon down toward the bottom of the periodic table is much more easily reacted than any of the other ones. There are no compounds made with helium, so helium is by himself. We've not seen helium with any other substance, always by itself. And I think that pretty much sums it up. So you've enjoyed Chapter 7, Lecture 4.